and on Zoom. For the first, okay, yeah, before we get started, I'll just say that this meeting is being recorded, so hopefully that's okay with everyone. I don't know how to get that off the screen because it's not on the screen. Oh, there. Okay, thanks. So yeah, thanks everyone for joining us today for the first sort of official ICE-THIC seminar. This is the first seminar that's really kicking off a series of seminars that will happen over the coming weeks and months. And today I'm really delighted to introduce Tim Crownshaw as our speaker. Tim joined ICE-THIC in January after finishing up his PhD at McGill University, where he was a participant in the Economics for Anthropocene research partnership between McGill, the University of Vermont, and York University. And that research partnership had a broad interdisciplinary focus with an overarching goal of reestablishing a mutually enhancing human-Earth relationship. Tim is originally from New Zealand and has a background in science and math and engineering, and experience working at a system operator, which is really valuable. He is a keen snowboarder and hiker, and also enjoys a good pint, which I think is a wonderful invitation to get to know Tim. So thanks, Tim. I'm looking forward to your presentation today.
Thanks, Madeline. Okay, thanks everyone for coming, and for those of you online. This seminar summarizes my PhD research, which explored the prospects of shifting the global energy system away from a predominantly fossil fuel basis towards greater reliance on renewable energy. It also touches on the issue of perspective regarding major environmental and socio-technical challenges, which increasingly need a different type of thinking from how they've been approached in the past. And I hope to unpack this a little bit. Okay, so to understand the prospects for energy transition, it is important to first position today's global energy system in its proper historical context. This chart shows the magnitude and composition of primary energy supply going back to the beginning of the 20th century. As you can see, global energy consumption has grown hugely over this period, increasing over 30-fold. Consumption has doubled since 1985 alone, and remains dominated by the fossil fuels, coal, oil, natural gas. Consequently, energy is still the largest source of global greenhouse gas emissions by a long way. Despite ongoing advances in renewable energy technologies, most notably solar photovoltaics and wind turbines, these technologies still account for less than 5% of the global supply mix, shown here in red. Essentially, the energy transition has only just begun. Expectations of future energy consumption span a wide range, from ongoing increases in line with historical trends to annual percentage declines driven by aggressive climate policy. Questions regarding what can be achieved and how quickly are critical, as energy is the cornerstone of the global economy. More fundamentally, energy is strongly linked with the maintenance of societal complexity, as noted by anthropologists Leslie White and Marvin Harris, among others. So it's hard to overstate what's at stake here. If we fail to successfully transition towards a sustainable energy system in time, we will not secure a viable future as a society. So we've all seen headlines like these. The prevailing narrative circulating in media, civil society, and government sources suggests that technological improvements and falling costs are leading to the exponential growth of renewable energy, increasingly disrupting the fossil fuel incumbents. And I think the implicit claim appears to be that we can have a modern industrial economy and way of life that looks much like today's, only better, but based on clean renewable energy, and we can achieve it relatively quickly. So as promising as this mainstream narrative may be, it does suffer from a number of conceptual weaknesses identified by a growing interdisciplinary critique. Energy transition is typically seen through distinct lenses or descriptive domains, including economic, technical, political, behavioral, and institutional lenses. There is no real overarching theory linking these domains together or a common understanding of what the global energy system fundamentally is. Epistemic limitations emerging from the high degree of uncertainty facing energy transition, are often ignored or downplayed in ways that provide a favorable reading of future prospects. For example, many major studies of energy transition assume the widespread deployment of speculative or unproven technologies in the relatively near future. Energy is frequently highly aggregated and assumed to be largely homogeneous, both in terms of quality and type. This ignores functional and temporal non-equivalences between distinct energy flows. Marginalist cost-benefit analysis based on market prices and ceteris paribus assumptions is central to many studies. This fails to capture the reflexive evolutionary nature of energy transition. A number of important physical aspects complicating the process of energy transition are either given cursory treatment or left out entirely, including primary energy resource constraints and depletion dynamics, infrastructural turnover and reorganization, and various balancing or negative feedbacks representing diminishing returns. Finally, mainstreamed narratives tend to focus on changes in the supply mix without giving adequate attention to the behavioral adaptation and demand-side investments required to unlock these changes. Overall, these shortcomings contribute to a relatively low level of public recognition of the potential degree of disruption and difficulty involved in a comprehensive shift to renewable energy. This is a situation that has been aptly described by Gianpietro, Mayumi, and Sorman as a clash of reductionism against the complexity of energy transformations. One way forward is to first identify the global energy system as an example of a complex adaptive system. Doing this allows an understanding of energy transition on a more robust theoretical foundation using established concepts and methodologies. So complex systems theory emerged in the mid-20th century as a transdisciplinary synthesis, largely from the fields of ecology, cybernetics, chaos and fractal mathematics, and non-equilibrium thermodynamics. A complex adaptive system is a type of nonlinear dynamical system composed of agents interacting within networks across multiple spatial and temporal scales with a given external environment. Within the system, agents interact with both integrative and self-assertive tendencies, creating feedback dynamics, self-organization in response to external stimuli, path-dependent evolution, and emergent properties at higher scales of organization. Complex adaptive systems also have the property of autopoiesis, or the ability to maintain and reproduce their essential structures over time. All biological organisms are complex adaptive systems, and so are the ecosystems they form. Human societies, too, are now increasingly recognized as examples of complex adaptive systems. So what are the attributes of complex adaptive systems that are relevant to the study of energy transition? Firstly, complex adaptive systems are always hierarchically nested within larger systems. The global energy system is fully contained within the wider human socio-ecological system, which is itself a subsystem of the biosphere. There are interactions and dependencies at all levels. As shown in this diagram here, the global energy system takes primary energy from the biosphere and returns degraded waste heat. Meanwhile, the human socio-ecological system supplies materials and labor to the global energy system, which in turn provides vital energy services such as illumination, transportation, and information processing to society. Energy cannot be understood in isolation, as all nested systems are subject to co-evolutionary processes. Secondly, complex adaptive systems are autocatalytic in nature. Energy production cannot be seen simply as a function of the conventional factors of production, capital and labor, as the provision of both of these factors requires energy. This means that a share of gross energy production must be diverted from dissipative or consumptive purposes and reinvested into the energy system's own internal processes and structures. This is known as the system's hypercyclic component. These flows need to be disaggregated with respect to all relevant functional distinctions. For example, flows of the main energy carriers, electricity, liquid fuels, and heat, must be considered separately to properly characterize the autocatalytic process. This attribute gives rise to strong path dependence. In particular, the energy system must produce sufficient flows across all necessary types to deliver energy services required by society while simultaneously meeting hypercyclic demands. Failure to do this represents a net energy trap, a situation where dissipative and hypercyclic components begin to compete, risking chronic deficit of energy carriers or even the collapse of the system itself. This phenomena exists in all complex adaptive systems. It's analogous to starvation in biological organisms, and the same thing can happen in society as a whole. Combining these attributes makes it possible to construct a view of energy as a complex adaptive system, shown here using an Odom flow diagram. These diagrams show the interrelation of energy conversion processes and stocks required for a system to function. Note that there is a linear dissipative flow of energy from the primary energy resources on the left to final energy services on the right via primary, secondary, and end-use conversion stages. Note also that the hypercyclic component, consisting of flows diverted from secondary output, and invested into system structures needed for these conversion stages to operate. As we've seen, the transition to renewable energy is historically unprecedented and remains very far from completion. The complex systems approach reveals that this transition is not only a major technical, economic, and political challenge, but is fundamentally a complex path-dependent socio-metabolic process. Any given pathway for system transformation of this kind can be characterized by two high-level descriptors. Feasibility indicates consistency with external constraints, including changing societal demands for energy services and declining primary energy quality due to progressive resource exploitation. The latter effect is illustrated in the diagram here to the right, showing an uncertain but negative relationship between cumulative energy production and energy quality as measured by EROI, or the net energy ratio. Viability, on the other hand, indicates consistency with internal constraints, which primarily in this case implies avoiding a net energy trap outcome in system collapse. So from this conceptual framework, a primary research objective can be posed to identify the solution space of energetically feasible and viable pathways for transformation of the global energy system from non-renewable dependence to renewable energy under uncertainty. To achieve this research objective, a suite of methods is required. Firstly, the chosen methods must be capable of representing dynamic change in a complex system with many feedbacks. For this, system dynamics modeling is ideal. Secondly, it is necessary to explicitly model pervasive uncertainty in model input parameters. Monte Carlo simulation is well suited for this. And finally, the selected methods must be able to integrate many diverse data sources and quantify the resulting strength of knowledge. Here, post-normal science offers useful tools, specifically sensitivity and diagnostic analyses. The resulting workflow looks something like this. Starting from the Odom flow diagram shown earlier, causal loop diagramming can be used to construct a detailed system dynamics model. Systemic data collection is then carried out to build stochastic definitions for all required parameters. Next, Monte Carlo simulation is performed to identify the solution space for energy system transformation. Sensitivity, diagnostic, and scenario analyses are being used to explore system leverage points and behavior under specific socio-technical narratives, and also identify model weaknesses arising from imperfect input data. The resulting probabilistic renewable energy solution space, or PRESS model, starts with a high-level global view of energy flows and conversions across primary, secondary, and end-use stages. Note that the provision of useful energy services is explicitly represented here, unlike in many studies, and energy carriers are disaggregated, including flows diverted into upstream power capacities for the production of energy carriers via an autocatalytic loop, and downstream power capacities for the conversion of energy carriers into final energy services via what's known as a capital hypercycle. This high-level view forms layer one of the model, which also includes submodules for energy service demand, model initialization, and process efficiencies. The second layer tracks the life cycles and utilization of all power capacity stocks required to facilitate the flows present in layer one. Modules here include system impacts from rising penetration of variable sources, EROI, and also the energy cost of capital. The third layer consists of an adaptive system control heuristic, which takes in information about the state of the system in each time step, forms a series of future supply and demand projections, and then modulates energy investment flows in layer 2. The goal here is to keep supply and demand in balance over time as efficiently as possible, while shifting towards renewable energy. Submodules here include optimization of intermittency mitigation, the detection of net energy trap outcomes, indicating transition failure. And since this is based in system dynamics methodology, the press model formulation is feedback rich and simulates path-dependent system evolution. It is fully probabilistic with distributions specified for all uncertain input parameters. It is primarily a physical model, so it does not directly include political, behavioral, or monetary barriers to energy transition. And for this reason, it is fundamentally exploratory in its design, not predictive. And in effect, it's designed to identify the solution space of best case, physically best case outcomes. The press model features 3,600 input parameters and over 14,000 output variables across 9 sectors and 11 subsectors. Okay, let's take a look at some model results. The first set of results presented here relate to the base case and summarizes an ensemble of 1,000 model realizations. An overview of flows through the global energy system at chosen snapshots in time can be given using Sankey flow diagrams. This diagram shows the situation as of 2015. Note that there is a dominance of fossil fuels in the supply mix on the left edge of the diagram, and on the right edge, you can see very large waste heat flows in black relative to delivered energy services in green. This can be compared to the mean flows for the year modeled for the year 2100. The first thing to point out is that while a shift towards renewables is achievable, fossil fuels will still likely play a major role by this time, particularly coal and natural gas. The good news is that a greatly improved provision of energy services is possible with much higher efficiency and reduced waste heat flows. This is possible via electrification of many end uses and improved passive system design. Also critical here is the shift from private vehicles to mass transit. Note that the autocatalytic loop, or energy invested into upstream production, shown in the top center of the diagram, is significantly larger in 2100 than in 2015. And this reflects the rising metabolic costs of reduced primary energy quality due to ongoing resource depletion. The mean modeled primary supply mix over time is shown here. So it is physically possible to strongly increase renewable energy use, as I mentioned, over the course of the century, and reduce total primary energy requirements and fossil fuel consumption. But after mid-century, further reductions do become more difficult, and rising energy service demands in most cases begin to drive total primary energy consumption upwards again, with significant contributions from coal and natural gas becoming necessary, as well as a large expansion of biomass energy. This can be seen another way by looking at the probabilistic distribution of total primary energy supply over the simulated period. There is a significant variation seen over the ensemble of 1,000 model realizations, with some exhibiting declines to a level of around 300 exajoules or so globally, and then staying relatively flat, while others increase strongly from around 2040, almost doubling by 2100. The composition of the global energy system changes drastically over all stages, primary, secondary, and especially in the end use sector. This is seen here in the mean mode shares for inland regional transportation, which exhibit a rapid shift away from the conventional internal combustion engine vehicle towards rail, and particularly electrified rail after mid-century. The mean mode share of electric vehicles also increases in green at the top there, but perhaps not as dramatically as some might expect. This chart shows the distribution of the share of total primary energy coming from renewable sources over time. This share can increase strongly from less than 20% currently to as much as 70% by 2100, although it may be limited to as low as 35% by this time. Notably, it doesn't appear to be physically possible to approach 100% during the simulated period. This chart shows the model distribution of global cumulative greenhouse gas emissions relative to the ranges of estimates given in the literature for carbon budgets corresponding to 1.5 and 2 degrees of warming. It doesn't appear to be physically possible to remain within these budgets through energy transition alone, even in the most optimistic case. However, the important thing to note here is that this doesn't consider the potential impact of deploying negative emissions technologies at scale. Sensitivity analysis is carried out for all epistemically uncertain model input parameters using a larger ensemble of 10,000 model realizations to identify inputs with a strong influence on results. Sensitivity is determined with respect to two selected transition results with strong implications for desirability: stable time, or the elapsed time before a net energy trap is encountered, and cumulative greenhouse gas emissions. A higher mean stable time is more desirable because it implies a lower risk of running into a chronic scarcity situation or system collapse. And obviously, lower cumulative greenhouse gas emissions are more desirable. Diagnostic analysis uses sensitivity results in addition to pedigree, representing the strength of knowledge associated with each input parameter. To assess pedigree, each input parameter is systematically rated on an ordinal 5-point scale across 3 dimensions shown in the table here to calculate a composite score. Sensitivity results for non-decision parameters over which no reasonable control can be exerted, unsurprisingly show the importance of primary energy resource magnitudes and qualities. In particular, the sustainable potential for biomass energy has a very strong impact on transition outcomes. More biomass energy available reduces the risk of a net energy trap, which raises an important potential trade-off between energy transition and environmental protection. Another dimension of this trade-off relates to coal. Greater coal resource magnitudes and higher quality are beneficial for avoiding a net energy trap, but strongly negative for cumulative emissions. Sensitivity results for decision parameters over which control can be exerted can be used to identify system leverage points and corresponding policy recommendations. So these results point to the need for aggregate energy service demand reductions to promote desirable energy transition outcomes. In particular, reducing demand for high temperature process heat and static mechanical work. Together, this represents the majority of the industrial sector. Is very strongly beneficial for reducing cumulative emissions and also for avoiding a net energy trap. Diagnostic analysis tries to identify input parameters with a combination of high sensitivity and low strength of knowledge. These results can point out productive areas for future research to improve the robustness of the model. And the diagnostic results again point to energy service demand, particularly in the industrial and transportation sectors. In addition to the base case, 6 scenarios investigate specific socio-technical narratives. These scenarios include the creation of a new inexhaustible low-cost source of electricity, such as nuclear fusion, strong regulatory constraints applied to emissions-heavy technologies, and most importantly, the implementation of optimal policies in line with system leverage points identified by the sensitivity analysis. This chart shows probability distributions for cumulative greenhouse gas emissions by 2100 by scenario. Most scenarios show a relatively minimal change in cumulative emissions relative to the base case, while no scenarios are able to keep emissions within the 2 degree budget range. Scenario 6 represents a systems-cognizant or systems-aware approach to policy design, and it does result in substantial reductions in emissions, potentially exceeding 1,000 gigatons of CO2 equivalent by 2100. In terms of stable time and the corresponding risk of a net energy trap, results indicate that scenario 4, representing aggressive top-down regulatory action to constrain emissions, is likely to be strongly detrimental, in addition to achieving only relatively modest emissions reductions. Okay, so to conclude, the emerging picture of energy transition is nuanced and complex. There is a non-trivial risk of encountering a net energy trap and associated disruptions before 2100. This risk is raised substantially if we either delay action or attempt to impose aggressive policy without understanding the solution space. Powerful environmental trade-offs exist, which may complicate environmental protection during the energy transition, particularly regarding coal and biomass energy. Reductions in demand for specific energy services, particularly in the industrial and transportation sectors, represent the best leverage points available to us. This implores us to really rethink current consumption norms and infrastructure design, and shift towards an ethic of achieving well-being within limits and an ethic of sufficiency. The rising metabolic costs of energy production will have far-reaching socio-metabolic implications, likely challenging expectations for continued economic growth this century. Scenarios suggest that while a systems-aware policy approach can vastly improve outcomes, there is no silver bullet in energy transition. Technological breakthroughs cannot be assumed to provide a complete solution. There is also serious unintended consequences associated with naive policy interventions. Overall, findings suggest that mainstream perspectives and expectations of energy transition may vastly overestimate the achievable pace of a shift towards renewable energy, while underestimating the extent of the associated impacts. Greater skepticism of common energy narratives appears to be justified. From a physical perspective, it is possible to reduce the consumption of fossil fuels, achieve major emissions reductions, and buy significant time for deeper cultural and behavioral changes. However, renewable energy is not likely to fully replace non-renewable energy this century, even allowing for drastic changes in patterns of energy consumption. Staying below 2 degrees warming is highly unlikely without the widespread deployment of negative emissions technologies, which remain speculative. So fixating on achieving 100% renewable energy in the near term may in fact be the wrong goal. Instead, there is an urgent need for policymakers and researchers to understand energy transition as a complex, path-dependent socio-metabolic process. Fostering a systems-based paradigm can bring energy transition research into a stronger theoretical footing and can help to navigate the challenges presented by global energy system transformation. All right, thanks for your attention.